Section 3 we're going to move through really quickly. We're just going to discuss which distributions you should use for each type of hypothesis testing that we're going to encounter in Chapter 9. So basically it's going to be the same two that we used for confidence intervals. Okay, the normal distribution in some cases, the student t distribution in other cases. So again, just like in Chapter 8, if we are talking about a mean and we know the population standard deviation, we use the normal. Okay, so we're going to use z-scores and one of the normal tests in the calculator. For means where we don't know the population standard deviation, we're going to use the student t distribution. Okay, this is going to be a t-test in the calculator. For number 3, if we're dealing with a proportion, then we're going to use the normal distribution again with z-scores, and the function in the calculator will be 1 prop z test. Just a quick note, we are only dealing with single means or single proportions. Okay, so we're not going to talk about comparing two proportions or two means yet. That's a Chapter 10 topic that I'm looking forward to talking about with you guys. In Section 4, rare events, sample, the decision, and the conclusion. So basically this is kind of putting the pieces together and trying to make sure that we understand how the process goes on hypothesis testing. So we've said this before many times, but now we're finally putting it into practice. If under a given assumption the probability of an observed event is very low, then we assume that the assumption is incorrect. So in this case, the assumption is going to be the null hypothesis. Okay? And if based on the data it looks like the null hypothesis is not correct, then we'll reject it, and we are putting the rare event rule into practice. Alright, so when using a sample to test a hypothesis, it's basically going to come down to one value. Okay, we're going to be looking for something called the p-value. And we're going to use the calculator to do this. I'm not going to make you do any hypothesis testing by hand because you're never going to have to do it by hand anywhere. So the p-value is just one of the numbers that the calculator spits out. It's the one we're going to pay the most attention to. Technically what it is the probability that if the null hypothesis is true, we would get results from a randomly selected sample that are as extreme or more extreme as the results that we got in our current sample. Okay, so basically what it's saying is, what are the chances that this sample is wacko? Alright, that's the p-value. What we're going to use the p-value for is as a comparison to the significance level. Okay, remember alpha is the significance level. It's also the probability of a type 1 error, and it's 1 minus the confidence level. Okay, so when we're doing hypothesis testing, we can either phrase things in terms of the significance level or the confidence level, and you should remember that alpha, the significance level, is 1 minus confidence. And here's going to be the big deciding factor. If the p-value is less than alpha, then we reject the null hypothesis. If the p-value is greater than or equal to alpha, then we fail to reject the null hypothesis. Okay, you might want to write that down in your notebook, circle it, star it, highlight it, whatever it is that you do to draw attention to things, because this right here is a very important guideline that I need you guys to know. If you have a hard time remembering it, there's kind of just a little silly way to say, to phrase this to help you remember. If the p-value is low, the null must go. If the p-value is high, the null will fly. Okay, so use it if you want, come up with a different one if you want, but sometimes these little silly things make it easier to remember. If so, go for it. Alright, so in example number 1, I'm just going to kind of walk you through the process of thinking about this, what distribution we're using, what we would put in the calculator, and all that stuff. So suppose a baker claims that his bread height is more than 15 centimeters on average. Several of his customers do not believe him. So to persuade them he is right, the baker does a hypothesis test. He bakes 10 loaves of bread. Mean height is 17 centimeters. The baker knows from baking hundreds of loaves of bread that the standard deviation for the height is half a centimeter, and the distribution of the heights is normal. So first thing we want to do is identify the null and the alternative. So a baker claims his bread height is more than 15 centimeters. So the claim on this one is mu is greater than 15. So the opposite of that would be that mu is less than or equal to 15. Alright, so now we can put these together in the null and the alternative, right? The null will be less than or equal to, the alternative will be greater than. Which distribution should we use? Well, we're talking about a mean, and we are told what the population standard deviation is because he said he's baked hundreds of loaves of bread. He knows the standard deviation is 0.5 centimeters. So we'll use the normal distribution and a z-test for this one. Alright, so without actually doing all the math, the p-value is very close to 0. Okay, so we'll say the p-value is like 0.00000001. Alright, so what should we do? What should we decide? Do we reject the null or do we not reject the null? Well, hopefully you remember, if the p-value is low, the null must go. So therefore we would reject the null hypothesis in this case. The null hypothesis lined up with the opposite of the claim, right? So therefore that means that the opposite statement is rejected, so the claim statement is supported. So all of that to say, it looks like the data supports the baker's claim that his bread height is more than 15 centimeters. For a second example, It's a Boy Genetics Labs claim their procedures improve the chances of a boy being born. Okay, so mother and father go to this lab to whatever procedure, and they say that they give you a better chance of having a boy, lower chance of having a girl. So the result for a test of a single population proportion works like this, okay, where we had a null of p is 0.5, okay, and we have an alternative that p is equal to 0.5. The reason that we're mixing an equals and a greater than here, which I told you we wouldn't do much, but the null actually kind of has a basis in like a common sense sort of situation here. We would assume under normal circumstances that the probability of getting a boy is exactly 0.5, right? There are only two choices for babies, it's boys and girls. So about 50% of the time it's a boy, 50% of the time it's a girl. So in this case it makes sense for our null to be an equals while our alternative is a greater than. Okay, that's one of the kind of rare cases. We're using a significance level of 0.01, and we do some math and we find a p-value of 0.025. So we want to make a decision, reject or fail to reject, and then interpret that and state a conclusion in a way that makes sense to people who aren't statisticians. So the p-value in this case is higher than alpha. So if the p is high, the null will fly, so we would say we do not reject the null, and so therefore it would appear that the data does not support It's a Boy Genetics Labs in their claim that the proportion of boys is greater than 0.5 using their procedure. Okay, if we fail to reject the null, that means the null is still hanging on. We're hanging on to the null. We haven't rejected it. And so we can't state with certainty that the alternative is true because the p-value is still sitting, or the null is still sitting there staring us in the face. All right, so the homework in this section is basically just trying to get you to do that. What's the null? What's the alternative? To be given a p-value and make a decision. Should we reject? Should we fail to reject? And then trying to write that conclusion. In section 5, we are going all the way from start to finish, doing a full hypothesis test and including them in the calculator part. So in every one of these, okay, you want to make sure that before you start, you know the significance level. And if none is given, then typically we use 0.05. That's the most common significance level. And then what we want to do is keep in mind that if the alternative uses a less than, then we have what we call a left-tailed test. If it uses a greater than, we have a right-tailed test. And if it uses a not equals, then we have what we call a two-tailed test. So that's important because we're going to put those symbols into the calculator. So in thinking about the p-value, if we assume that alpha is 0.05 for a moment, remember that if the p-value is low, then like really low, then we can be confident in rejecting the null. But if the p-value is just a little bit low, well, that might change the way we phrase our conclusion. Okay, so if you got an alpha of 0.05 and a p-value of 0.01, for sure, that's a good result. We definitely reject the null without question. If it's 0.046, we still reject the null, but we'd probably make some kind of a comment in our conclusion that, that it just barely snuck in there with significance. All right, so on the other hand, say you have, you're going to decide not to reject the null. Well, there's two scenarios here that are very different as well. So you might have a p-value of 0.4, okay, not 0.04, but 0.4, which is way bigger than 0.05. And so we would definitely say no, definitely fail to reject the null. Clearly the null hypothesis is possible here. On the other hand, we might have a p-value of 0.052, which is just barely higher than the alpha. And so, we would decline to reject, but we might say, the sample just missed out on significance. So, in all cases, right, your own reasoning skills are better than just blindly following math rules. So, you might not be comfortable rejecting 0.049, right? Even though technically, the rule is we reject the null hypothesis if we're less than alpha, but if it's that close, you might go, I'm just not comfortable rejecting the null hypothesis with this. So use your own common sense. All right, so here's our full example number 1. Jeffrey is an 8-year-old swimmer, okay, and he has a mean time of 16.43 seconds over his career swimming as an 8-year-old. That's not a very long career, but nevertheless. And he has a standard deviation of 0.8 seconds. So his dad got him some different goggles, thought it might make him swim faster. So in 15 swims, 15 25-yard swims, he had a mean of 16 seconds. Okay, so Frank, his dad, thought that the goggles helped, okay, because he swam faster faster than 16.43 seconds. So we want to do a hypothesis test on this, all right? So I'm going to walk you through the steps. Okay, first of all, we're dealing with a mean, okay? So that means it's either a z-test or a t-test. We know the standard deviation sigma, so that tells us it's a z-test. All right, and in fact, we're going to use z-test in the calculator. So in the stat menu, you'd hit stat, you go over to tests, and you're looking for z-test. Next, we want to write out the null and the alternative hypotheses. So we've walked through several of these, so I think I'm just going to kind of fly through this part a little bit fast. The null hypothesis, mu is greater than or equal to 16.43. Alternative is that it's less than 16.43. Our significance is 0.05. Excuse me, our significance is 0.05. And if you go to the calculator and do z-test, okay, let me kind of walk you through this. Let me look at my calculator as we go. Stat, go over to tests. Z-test is the very first option in the list, so that's nice. We want to select stats for this one. Our mu0 is the mean that shows up in the null hypothesis. So 16.43 would be mu0, okay, mu naught. Our sigma, we are told, is 0.8, okay, so put that in. And then x bar is the sample mean. So for the 15 swims that Jeffrey did, his mean was 16. Okay, so x bar is 16. And then n is the number in the sample, which would be 15. Okay, he swam 15 times. All right, now in the bottom line there, it says mu colon not equal to mu naught, less than mu naught, greater than mu naught. We want to match the symbol in that row to the alternative hypothesis. So our alternative is a less than, so we select the second option, the less than. Then we hit calculate, and you should see a p-value of 0.01868, and it keeps on going, but I rounded it off there. It also tells you the z-score, negative 2.08, and but the thing that we're really looking for is the p-value, 0.01868. So with that p-value, comparing it to the alpha of 0.05, pretty clearly we would reject the null hypothesis. All right, and in this case, rejecting the null hypothesis supports the alternative hypothesis, and the alternative hypothesis supports, or is the a restatement of Frank's claim that the goggles helped. So, final conclusion, the data supports Frank's claim that the goggles helped Jeffrey to swim faster. All right, so there's example number 1. In example number 2, we have stat students who believe that the mean score on the first statistics test is a 65. Okay, a stats instructor thinks that the mean score is higher than 65. So he samples 10 stat students and obtains the scores 65, 65, 70, etc., etc. Okay, he performs a hypothesis test using a 5% level of significance. That's the same thing as saying that alpha is 0.05, and the data are assumed to be normal. So this is a test of a mean, but this time we are not given the population standard deviation. Okay, so we're going to have to use a t-test. And you may have guessed that we will use the t-test function in the stat menu. So stat over to tests, t-test is the second option. Okay, again, our null, kind of going quickly here, mu is less than or equal to 65, and the alternative is that mu is greater than 65. You could argue on this one that the null should actually be equals. Mu is equal to 65 because that was the student's claim, right? The students believed it was 65. The instructor believed it was greater than 65, so you could have used those two. I decided just to focus in on the instructor's opinion because he's the one that it says is performing the hypothesis test, but that's arguable. All right, so alpha is 0.05, and if you go through the t-test procedure, if you hit t-test, this time we're going to tell it data. If you haven't already, you need to put those data values from 65 to 71 there in that middle of the screen. You need to put that into L1 and then come back to t-test. Okay, select data. The mean there, the mu naught is 65. The list is L1. Frequency is 1. And then we want to select the greater than on the last line because the greater than symbol is what we see in the alternative hypothesis. So then we calculate and we get this p-value of 0.0396. So once again, we would reject the null hypothesis and support the claim of the instructor. All right, so in example number 3, we have June, who believes that 50% of first-time brides in the United States are younger than their grooms. So she performs a hypothesis test to determine if the percentage is the same or different from 50%. So she samples 100 brides, 53 reply that they are younger than their grooms. She uses a 1% level of significance this time. All right, so this is a test of a proportion, right? And that's not a mean anymore. We're talking about the percent of people who are a certain thing, okay? So we're going to use z-test again, but this time it's one prop z-test for one proportion z-test. In the menu, that is option 5. One prop z-test is number 5. Our null is going to be that the proportion p equals 0.5. The alternative will be that p is not equal to 0.5. We're using a 0.01 alpha, and if we go through and punch some numbers into the calculator there, our p naught is 0.5, our x is 53, our n is 100, and we want to select not equal to, and we should get a p-value of 0.5485. So with a p-value that is that much higher than alpha, we can with confidence say that we should not reject the null hypothesis, and therefore we say that there's not enough evidence to reject June's belief that 50% of brides are younger than their grooms. Okay, it's tempting to say that the data supports June, okay, but kind of like what I was saying before with reject versus not reject, or reject and fail to reject, we can't go so strongly as to say that the data supports an equality statement, okay, because June's claim is really a statement of equality. And so kind of like we've talked about, where the probability of an exact value in a normal distribution is technically 0, because probability in normal distributions is area. And if we have an area that is just a single digit wide, it's basically 0 wide, then we're not going to have any area. So we can't make strong statements like that about equality. The best we could say is there wasn't enough evidence to reject June's claim. Okay. All right. So your homework on this one, I gave you a little bit more, and I pulled some from the homework section as well. Hypothesis testing is really important, and I know I fit a lot into just 2 videos in this chapter, but I wanted to try to get it to you as quickly as I could so that you can get as much practice in as you can before the quiz at the end of the week. So please let me know if you have any questions, and talk to you soon.